Welcome to the video on bias compensation, which is one of the important topic in Unit 2 of Electronic Circuits 1 subject. Now we'll see what is bias compensation. I hope you might have all known about different stabilization techniques in biasing. All the stabilization occurs due to negative feedback action. This negative feedback, although improves the stability of operating point, it reduces the gain of the amplifier. So in order to have this gain of the amplifier, we go for this bias compensation techniques. So see here, as the gain of the amplifier is a very important consideration, some compensation techniques are used to maintain excellent bias and thermal stabilization. Okay. So now we are going to see some bias compensation techniques. The first one is diode compensation for instability. The next one is thermistor compensation. And finally we have sensistor compensation. So first we'll see what is diode compensation for instability. These are the circuits that implement compensation techniques using diodes to deal with biasing instability. The stabilization techniques refer to the use of resistive biasing circuits which permit IB to vary. IB means base current, okay? IB to vary so as to keep IC relatively constant. IC means collector current, okay? There are two types of diode compensation. The first one is diode compensation for instability due to VBE variation, okay, base emitter voltage, and diode compensation for instability due to ICO variation. So first we'll see the diode compensation for instability due to VBE variation. So you can look at the circuit diagram here. Normal voltage divider biasing circuit where the diode D is attached here, okay, and it is being biased by using this VDD voltage, and the voltage across the diode is VD, and you have a resistance RD, okay. So now let us see how this diode compensation for instability due to VBE variation is going to work. So in a silicon transistor, the changes in the value of VBE results in the changes in IC, okay. A diode can be employed in the emitter circuit. See, can you see? Only at the emitter region this diode is attached. So a diode can be employed in the emitter circuit in order to compensate the variations in VBE or ICO. As the diode and the transistor are of same material, so you have to be careful that diode and this transistor should be of same material. The voltage VD across the diode has same temperature coefficient as VBE of the transistor. Okay, that is what being told here. See, the diode is kept biased in the forward direction by the source VDD and resistance RD. If the diode is of same material and type of transistor, the voltage V0 across the diode will have the same temperature coefficient as the base emitter voltage. Now, if you apply KVL around the base circuit, you get this expression, okay? So since VBE tracks V0, that is output voltage with respect to temperature, then IC will be insensitive to variations in VBE. Okay. So the current IC remains constant in spite of the variations in VBE. So this is how we are maintaining the collector current constant. Next, we are moving on to diode compensation for instability due to ICO variation. Okay. So for ICO variation, the diode is attached over here in place of the R2 resistor. Okay. So now let us see how this is happening. The reverse saturation current I0 of the diode will increase with temperature at the same rate as the transistor collector saturation current ICO. Actually, you know what is ICO, right? ICO is the collector saturation current. So they say that the reverse saturation current I0, okay, this is of the diode, will increase with temperature at the same rate as the transistor collector saturation current ICO. The diode D is reverse biased. This is actually reversed biased, okay, by VBE, and the current through it is the reverse saturation current I0. So let us see the expressions for that. So, you know, normal I current, we have I is equal to VCC minus VBE by R. Actually, usually write I in terms of V by R, right? So, you have got this VCC, that is biasing voltage, and minus this base emitter voltage divided by R. So, this is going to be very, very small, so we are neglecting. So, it is finally approximately equal to VCC by R, which is a constant. And you know the current I is actually the summation of IB plus I naught, that is the reverse saturation current of the diode. Now, the base current is given as, from this you can easily get base current, right? IB is what? I minus I naught. And we also know that collector current has got a general expression as beta IB plus 1 plus beta ICO. So substituting the above value in the expression for collector current. Yeah, you know IB value, right? Yes. Substitute in this expression. You get this. So suppose beta is very, very greater than 1. Okay. Then and therefore this I naught is also equal to ICO. Then you will get the final expression as IC is equal to beta I. Okay, so I is almost constant, and if I naught of diode and IC of the transistor track each other over the operating temperature range, then IC remains constant. Now next we can move on to the thermistor compensation technique. Actually, these are the other compensation techniques which refer to the use of temperature sensitive devices such as diodes, transistors, thermistors, sensistors, etc. to compensate for the variation in currents. So the two popular circuits used in this method, one using a thermistor and the other using a sensistor. So let us have a look at it. So first we'll see what is a thermistor compensation, okay? So can you look at the circuit diagram here? The thermistor is actually added over this region. Thermistor is a temperature sensitive device. It has negative temperature coefficient. The resistance of the thermistor increases when the temperature decreases, and it decreases when the temperature increases. That is what you call it as negative temperature coefficient. Okay. In an amplifier circuit, the changes that occur in ICO, VBE and beta with temperature increases the collector current. So the thermistor is employed to minimize the increase in collector current. So how can you still more understand this? See, as the temperature increases, the resistance RT, can you see? RT of the thermistor decreases, which increases the current through it, and the resistor RE. Now the voltage developed across RE increases. Okay, where is okay? Can you look at this point? The voltage developed across RE increases, which reverse biases the emitter junction. This reverse bias is so high that the effect of the resistors R1 and R2 providing forward bias also get reduced. This action reduces the rise in collector current. Thus, the temperature sensitivity of the thermistor compensates the increase in collector current occurred due to temperature. I hope you would have understood. So, you have to attach the thermistor only across this portion so that you will get the stabilization and IC remains constant. Next, we are moving on to sensistor compensation. Actually, sensistor is a heavily doped semiconductor that has positive temperature coefficient. So positive temperature coefficient means the resistance of the sensistor increases with increase in temperature and decreases with decrease in temperature. So that is why we call it as a positive temperature coefficient. So now let us see the figure or the circuit diagram of a sensistor compensation. Yeah, you can see a sensistor attached in this region. The sensistor may be placed in parallel with R1 or in parallel with RE. Anywhere you can place. As the temperature increases, the voltage of the parallel combination and R1 increases, and the voltage drop also increases. Okay. So the resistance of this parallel combination as well as the sensistor also gets increased, and their voltage drop also increases is the first point. This decreases the voltage drop across R2. Due to the decrease of this voltage, the net forward emitter bias decreases. Okay. As a result of this, IC decreases. So hence by employing sensistor, the rise in the collector current, okay, which is caused by the increase of ICO, VBE and beta due to temperature gets controlled. So I hope by watching this video, you would have understood clearly about this bias compensation techniques. Thanks for watching.